Hi everyone, my name is Devi Parikh. I hope you're all doing well. It's too bad that we couldn't be with each other in person, but hopefully we can do that again sometime in the near future. I hope you're all safe and thanks for tuning in to listen to my talk. And so I'm going to talk to you today about some work we've been doing with multimodal AI systems and creative AI systems. And so let me start with the first part on multimodal AI. And by that, I mean vision and language. And so I mean tasks like given an image like this, we might want to automatically describe it in a natural language sentence like you see here. Or given an image like this, we may want to describe the different regions in the image in brief descriptions like you see on the screen. Or given an image and a natural language phrase like the toy with pink hair, we may want to draw a bounding box around the region in the image that's associated with this description. And it might not be just static images. There might be a video that we may want to describe in high levels of detail, like you see here, or perhaps a shorter description in a few sentences, or even a single sentence description that captures the gist of what is going on in the video. It may not just be descriptions. We might want systems that can answer natural language questions about images. For example, what is the kid doing? We may want to be able to answer this question automatically and say the kid is skateboarding. And it might not be just a static single question, but there might be a back and forth conversation where the system might start with a description of the image and the user might have a follow-up question. Is the motorcycle moving or still? The system might answer its part, and this conversation can continue from there. And so the reason these problems at the intersection of vision and language are interesting is because there are several applications that can benefit from these. So for example, for aiding visually impaired users who may not have access to the visual modality, if we have a way of translating from this visual modality to language, then through language, these users might be able to extract information about the visual signal. If you want to navigate through large quantities of unstructured data, language is a natural modality with which you can interact with it. A lot of the information on the web is inherently multimodal. And so having ways of connecting vision and language can allow us to extract information, richer information from the web. A lot of the content that might be on the web, if you want to identify hateful content, these problems tend to be inherently multimodal, but it's not just about the vision, it's not just language, but you need to reason about both to be able to make these assessments better. If you think of AR, VR applications, again, having the visual world and language connected can be useful for these applications. And so in this space, we as a community have made a lot of progress. We can now take images like this and automatically describe it as a man in blue wetsuit is surfing on the wave, or an image like this, a group of young people playing a game of frisbee, or a car is parked in the middle of nowhere, a pot of broccoli on a stove. And these are all automatically generated descriptions as of a few years ago, which is quite impressive. Even in visual question answering, we can take images that look like this. And if there's a question that says, what is the cat wearing? We can automatically answer it by saying a hat. Or for this image, what is the weather like? We can automatically answer it saying rainy. What surface is this? Clay. What is the weather like? Sunny. What color is the cat's eyes? Green. What toppings are on the pizza? Mushrooms, and so on. And so we've made a lot of progress on a variety of these tasks over the years. But one thing that has led to this progress is this recipe of training task and dataset specific models. So for every task that we care about, let's say visual question answering, a group of researchers, in this case, my students and I, we collected this large data set on visual question answering and we trained models specifically for that task. And so now we then had a model that can answer questions about images. But now if we want to do image captioning, then we sort of follow the same thing again. We collect a new data set for image captioning, train a model specifically for that task, and then we can have an image captioning model. Visual common sense reasoning or referring expressions. So for any one of these tasks, we collect a separate data set, we train specific model architectures, and that's how we've made progress on many of these tasks. And so what's dissatisfying about this approach is that you would think that there is a common set of visual linguistic representations that you can just learn. You can learn them once, and then you should be able to apply these to a variety of tasks. And that's not what's been happening. For each of these tasks, we end up learning a different set of visual linguistic representations. And so as a result, what might happen is if you ask a VQA model, what is the man making? The VQA model might say cake, which is not quite right, but that's what it thinks. And if you feed this image to a captioning model, the captioning model might say an older man is wearing an apron and making pizza. And so this suggests to us that these two models have learned a different set of grounding for the regions in the image. The VQA model thinks this image is about a man making cake, but the captioning model thinks this image is about a man making pizza, which is not quite consistent and is in that sense quite strange. So what we wanted to do was to see if we can learn a common model for visual grounding. And so once we learn this common model for visual grounding, we can use it for a variety of visual and language tasks. And so that's where we had this model called Wilbur that we presented at NeurIPS in 2019, where the setup that we were looking for is we wanted to be able to pre-train these visual linguistic representations, so pre-train these connections between vision and language once. So you do this pre-training once, and then you can fine-tune this for a variety of downstream tasks that you might care about, whether it's answering questions about an image or image and caption matching or any one of those things. And so one thing we need to think about if we want to pre-train these visual linguistic representations is what source of data we can use to train these models. And so in this work, we used conceptual captions that has 3.3 million images and associated descriptions from the web. Another thing to consider is that the two modalities, vision and language, tend to be at two different levels of abstraction. So on the vision side, sort of these low-level pixels, each pixel individually doesn't have much semantic meaning. Whereas on the language side, if you look at individual words, each word already is fairly rich in terms of the meaning that it captures. And so we need ways in which to bridge these two modalities and deal with the fact that they can be at two different levels of abstraction. And so we propose this two-stream model that tries to work with this, and the details of that are in the paper. Another thing to consider is how we can combine information across these modalities. And so we have a co-attention mechanism that, based on the visual information, attends to language in an appropriate way. And based on the language, it attends to the visual signal in an appropriate way. And so with all of these pieces together, we're able to pre-train these visual linguistic representations and then apply them to 5 different downstream tasks. And what we found at the time was that this approach outperforms state-of-the-art on all 5 tasks. And what's nice about this is that all of these tasks have a common backbone, a common set of visual linguistic representations that are consistent across all of these tasks. And you then have this downstream performance that is very accurate. So that was nice to see. We then extended this work where instead of pre-training the model to learn these visual linguistic representations and then fine-tuning it for each of these different tasks, we wanted to see if we can have the same model be applied to a variety of different tasks. And so in this case, we had one model for 12 different tasks. And what we found was that this performs higher than what you would get if you had trained an individual model for each of these tasks. And so what that means is you essentially have higher performance for 1/12 the model size, which was quite nice. And on 7 of these tasks, we had state-of-the-art performance. And so now you have one model that, given an image and a question, can answer the question. Given an image and a caption, it can give you a score for how consistent the two are. Given an image and a phrase, it can draw a bounding box around where that region is described, and a variety of other things that you see on the screen here. So what I will do next is I'll show you this online demo that we have. You're welcome to check it out yourself. It's on billboard.cloudcv.org. You can upload your images and try a variety of tasks. And so here, let me walk you through this demo on a few examples where we can first upload an image. And as I said, you can try this with any images that you like. And now on this image, you can pick one of these several tasks. Here we're going to ask a question that says, where is this picture taken? And so this model says kitchen. On the same image, we can ask a spatial reasoning question, like what is behind the man? And the model says refrigerator. We can now do a pointing question, like which object is red? And the model will point to the different objects in the image that are red, like the t-shirt and the apple and so on. You can do a referring expression where you give it a phrase like the boy, and the model is expected to draw a box around that object. So you see that you're seeing a box around the boy. If you now make it the girl, you should see bounding boxes around the girl in the image. We can do a referring dialogue where we can now ask for an object that's edible and is red. So is it edible? Yes. Is it red? Yes. And so it finds the apple, which is the red object in the image that's edible. If I now say, no, it's not red, but it is still edible, the box is now around the bananas, which are edible but not red. We can do a visual entailment where we can give it a statement, and the model will tell us whether the statement is a contradiction or neutral or true with respect to that image. We have some tasks that need 2 or more images. So here's a task that needs 2 images that we just uploaded. And for this pair of images, we'll give it a caption that says both images have 3 people in them. And the model says that's false because it's not true. It's not the case. The image on the left has 3 people in them. And the model says that's true. And if you now say the image on the right has 3 people in them, the model should say that's false. We'll now do one last task where we upload these 4 images. And it's a retrieval task. So I will, as input, provide a description, and the model will sort the images based on how much they match the description. So mother and daughter, and the model will now sort the images based on which image is closest to a description of mother and daughter, father and 2 kids. The model is resorting the images for this description. That makes sense. Street scene. And so these same 4 images are being sorted based on the input description, the input query that we're providing. And you can see that the responses are quite meaningful. A peaceful scene. Boy is handing a can to a man. And so the top left image should be the most relevant to that. And that's what the model says. A girl is flying a kite on the beach. And so you can see that the descriptions can be somewhat abstract, like a peaceful scene, or it could be naming the scene or the objects that are in the scene and so on. And so that those descriptions have been reasonable. And so, as I said, you're welcome to check this out yourself. In this project, we're interested in taking as input a piece of music and producing a visualization or a set of movements where the movement is synced with this input music, and so it has this illusion of being a dance, if you will. So this is one example where I'll play the music that was the input piece of music, and you will see this abstract pattern move in a way that hopefully looks like it is synced with that music. And here's another example where it's the same approach, it's the exact same algorithm, except the visualization now, instead of being this abstract pattern is a stick figure of a human. And so this might look a little bit closer to what we're used to thinking of as dance. And so I'll play this again, where you'll hear the input music, and the stick figure will move in a way that should roughly look like it's synced with this music. And so one project that we have in this space is called Thematic Typography, where given a certain word like book and a theme library, we want to write the word out in that theme. So in this case, we are replacing the letters of the word book with icons that look like those letters, but are actually pictures that represent the theme library. So here's another one. The word is car, and the theme is driving or road signs. Here's another one where the word is witch and the theme is Halloween, or the word is play and the theme is Olympics. This is another project that we've done in this creativity space that's called Lemotif, where as input we are given a description from a user of what their day was like, and we can automatically extract what the topics were that were being discussed in this description and what emotions the person seems to be describing around those topics. And we generate automatically this visual abstraction where the topics are displayed as these different shapes and the emotions are displayed through these different colors. And we have this visual abstraction based on that. This is one visualization. We have several others that we've experimented with, but that's the general idea. We've also done some work on neuro-symbolic generative art, where we start with generative art or visual patterns that have been produced by a procedural generative process. And then we train a neural generative model on top of that to produce these visual patterns that have this different organic aesthetic to them. That is a combination, sort of a hybrid of the neural generative aesthetic and the procedural generative aesthetic with which the original training data was generated. We've also done some work on looking at collaboration in the context of creating sketches, where there's one canvas and different people can come one after the other and contribute strokes to this canvas to create a picture. And we've studied what happens in different collaborative settings. So at one end of the spectrum, you have this individual setting where one person has drawn the entire picture. And what we find is that there tends to be a variance in quality based on the skill level and the motivation of the individual creating this picture. Where some of these are quite nice, whereas other ones are perhaps not all that nice. But overall, it sort of tends to be a little boring that even when the picture is nice, the topics and the themes might be similar to what one might expect. The other end of the spectrum is where multiple people have all contributed to a picture. So one after the other, 30 different people come in and contribute strokes to the canvas. And what we get looks something like this, which is quite intriguing. It's very different from the pictures that you see on the left, but it tends to be sort of a little too chaotic and too noisy to extract any meaning out of it. And so we propose this in-between setting that has this collaboration component, but also has a voting mechanism, which gives us these interesting and rich pictures, but they're also quite coherent and sort of they tend to be less noisy and less chaotic. And so all of this was studied in the context of human-human collaboration, but the hope was to be able to extract, to be able to learn from what we find here and use that to design human-machine collaborative systems. And so to summarize this part of the talk, I think creativity is important. It's at the core of all progress that we make. Creativity is also sort of considered to be a deeply human experience. And so if we can have ways in which AI can assist humans in this creative process, that can be quite powerful. It's an intriguing AI challenge. As I said, it's a powerful use of technology. And at its core, it has human AI collaboration, which I think is quite exciting. So overall, to summarize my talk, I talked about two different themes within this context of human-centered AI. The first was problems at the intersection of vision and language. which can be thought of as having natural language interfaces with these computer vision systems. And the second is this idea of trying to use AI as a way of assisting or enhancing human creativity. That's all I have. Thank you.